everyone. In the previous session, I have discussed about the relationship between the line values and the phase values. Okay, so both in star network and delta network. Okay, that means both in star connection and delta connection. In this session, we'll see how we can calculate or how we can measure the power in three-phase system. And as you know already, for a single phase, okay, that is for each phase, the power can be expressed as Vi cos phi, as we have derived in the single phase chapter, that is single phase system. Okay, so power can be calculated as, or power can be expressed as Vi cos phi. And in three phase, as we have already understood the concept of star connection, so power can be considered as, because star connection, we have discussed star connection in three-phase system. Okay, so here for single phase or for each phase, the power can be expressed as Vi cos phi. Then for three-phase system, that is in star connection, we can have the power as 3 times of Vi cos phi. Since we are calculating power for three-phase system, so we can express P is equal to 3 times of Vi cos phi, and this V is nothing but, again this is Vph and this is Iph. Okay, so this is per phase. And now we can express, so now we are considering for star connection, and you know that in star connection, so Vph is equal to VL by root 3, as we have derived in the previous session. VL is equal to root 3 Vph in star connection, and IL is equal to Iph in star connection. Okay, so this we have already derived in the previous session. So VL is equal to root 3 Vph, IL is equal to Iph. So now I am just replacing this Vph in terms of VL, that is VL by root 3. And what is Iph? Iph is equal to IL. Okay, IL cos phi. And further, if we simplify, so you know that, so this 3 can be expressed as root 3 into root 3, right? So VL by root 3 and IL cos phi. So root 3 gets cancelled. So finally the total power P is equal to root 3 VL IL cos phi. So this is the power in three-phase system for star connection. Similarly, so let's look into the delta connection. In delta connection, so again P is equal to, again it is 3 times of Vi cos phi. So remember, this is for each phase, so Vph and Iph. And in delta connection, we know that Vph is equal to VL. Vph is equal to VL in delta connection. So straight away you can replace this Vph as VL, and Iph is equal to IL by root 3. So in delta connection, IL is equal to, we have derived. So we have derived in the previous session as IL is equal to root 3 Iph. So what is Iph? IL by root 3 and then cos phi. So further, if you simplify this expression, so we get P is equal to root 3 VL IL cos phi. So remember, both in star connection and delta connection, the three-phase power or power in three-phase system. Okay, so power can be expressed as root 3 VLIL cos phi. Again in delta connection also, P is equal to root 3 VLIL cos phi. Now let's see how we get this equation using wattmeter method. So next we have measurement of power in three-phase circuit. Okay, measurement of power in three-phase circuit. So using wattmeter, and this we call it as wattmeter. Meter is the instrument which is used to measure, the power in electrical circuit. Okay, I'll just repeat, wattmeter. So this is nothing but wattmeter, and wattmeter is the instrument which is used to measure the power in electrical circuit, and this wattmeter consists of two coils. Okay, so you can just look at the figure. So here wattmeter consists of two coils. One we call it as current coil, and which is named as CC, and another coil as potential coil. Okay, which consists of two coils. One is current coil which is connected in series to the circuit. So you can just observe this coil, and which we call it as current coil, and this is connected in series. So this is the supply. Okay, so here we have a supply, and here at the other end we have got a load. Okay, so in between we have got two coils, and one coil, that is current coil, which is connected in series to the circuit, series in the circuit where the current flows through it. Okay, where the current flows through the coil. So this we call it as current coil, and another coil we call it as potential coil. Potential coil, so is connected across the circuit. So you can just look at this. One end is connected here, the potential coil. Okay, the one end of the potential coil is connected here, and other end of the potential coil is connected here. That means the potential coil is connected across the circuit or across the supply. So it has got two coils, current coil and potential coil. So wherever we consider wattmeter, so if we are going to have these two coils in the wattmeter. And so here we know that in a single phase, for example, if a single phase is connected in each phase, that means to say, so single phase is connected, let us consider, so like W1, the wattmeter reading for a single phase, and similarly so another wattmeter, because to obtain power for three individual phases. Okay, to obtain power for three individual phases, then how we can calculate? So W1, that is wattmeter reading. Okay, so wattmeter reading for single phase, and wattmeter reading for the second, so that is again single phase. To find the power for three individual phases, each phases, then we can have W1 plus W2 plus W3. Similarly, but here to measure the power for three-phase circuits, only 2 wattmeters are enough. So remember, trying to explain here is, whenever to find the power using three individual phases, then we should have 3 wattmeters. Okay, W1 plus W2 plus W3. But to measure the power, for three-phase circuit, only 2 wattmeters are enough. So now we are going to demonstrate. So we are going to find, or we are going to calculate the power having only 2 wattmeters. Here you know how to write a star circuit. Okay, so star connection, how to make a star connection using 3 loads. So here we have Z1, Z2, Z3, and of course this is the neutral point. Okay, already we have seen the similar circuit in the relationship between the phase values and the line values. Okay, in star connection, the same circuit. So you can see here, and here, so we are going to find, or we are going to measure the power using these 2 wattmeters, which are W1 and W2. Okay, so W1 and W2, and so the question is, so where we should have these wattmeters? Okay, W1 and W2, and you can see here, so there are 3 connections, R, Y, B, and R is connected here, and this is Y, and this part is B. Okay, and this is the neutral one. Now, so where we should have the wattmeter? So remember, wattmeter consists of 2 coils, one is current coil and another one is voltage coil or the potential coil. So here, and out of these three, that means R, Y, B, so we can have 2 wattmeters at any point. Okay, so here I am going to have wattmeter, so 1 wattmeter, and so let's consider the coil. Okay, so this we call it as current coil, and another one is voltage coil. Remember, okay, each wattmeter should have two coils. One is current coil, where the current coil is directly, it is connected in series to the supply, okay, because we know that these three are the lines, that means line supply. So here the current which passes to this current coil as IR. Okay, why it is IR? Since we have taken at point R, so we can represent this as IR. So the current is entering this current coil. Of course, the current coil should be connected in series to the line. Okay, and another coil we have, so this we call it as what? Potential coil. And the potential coil should be connected across the supply or across the circuit. Across means the one end is connected here. Okay, the one end of the potential coil is connected here, and the other end of the coil should be connected to this B. Okay, not necessarily B. So here we have taken B as a reference. As I have already told you, so we are going to have only two wattmeters, W1 and W2. We are going to have only two wattmeters, W1 and W2. Okay, anywhere in these 3 points, that means RYB. So here one wattmeter is constructed at the point R. So that means the current coil is directly given to this R and the potential coil. So one end is given to this point and other end is given to B, because we have taken B as a reference. Not necessary B always at B. So if we consider another wattmeter at B point, then we can have Y as a reference. I hope this part is clear. So next, and this we call it as, let us call this as W1. Now the first wattmeter is constructed, and similarly, so we should have another wattmeter W2. Then the question is, where should we have another wattmeter? So if we have taken B as a reference, another wattmeter should be constructed at this point Y. Okay, so now again, now this is current coil. Right, so we know that the wattmeter should consist of two coils. One is current coil, which is directly, okay, connected to the line, and another coil is voltage coil. So one end of the potential coil or voltage coil is connected to this Y, and another end of the potential coil is given to B. Okay, so now let us call this as W2. Okay, even though we have 3 lines R, Y, B, but we can have only 2 wattmeters, so we can choose any point out of these 3. But in this case, I have chosen at R, and another one I have chosen at Y. Okay, I have taken B as a reference Okay, that is ground point. So I'll just recall this. So current coil, which is directly given to the line R, and the potential coil, one end of the potential coil is connected here, other end of the potential coil is connected to B. Okay, you can just see here. See, if you just mention like this, so it is not directly connected to Y, it is directly connected to B. And similarly, so we have another wattmeter which is at Y. So current coil is directly given to Y, and the potential coil, one end of the potential coil is connected here, and other end of the potential coil is connected to B, because B is the reference one. And once the construction is made, right, so I hope it is clear. So we have star circuit, so it is connected in star form. Then later we can have 2 wattmeters, so one is at R and another one is at Y, and B is taken as the reference one. So once the circuit is made, then we have to analyze the circuit, okay, to prove the equation √3 VLIL cos phi. Now the single phase power measured from W1 can be written as, so power measured from this W1, that is from the first wattmeter. We know that the power can be expressed as VI cos phi, right? So of course VLIL cos phi. Now, so what is line voltage here? Well, the line voltage is nothing but the voltage is measured between this R to B. Okay, so it is VRB. Similarly, what is what is the line current here? The line current means the current which is coming out of this line. Okay, that means R. So we can have this as IR. Right? So one is VRB, which is the line voltage. The voltage is measured between these two lines R and B, and the line current is IR, because the current coil is connected to R. So we have the current called IR. And so this phi is nothing but, so we are going to find the angle difference between this VRB and then IR. Okay, if we find the angle difference between this VRB and IR, so then this becomes the angle, okay, that is phi. So and similarly, so this is, let us call this equation as 1. And similarly from the second wattmeter, how we can have the power or the reading? So W2. So W2 means, so what is line voltage here? The voltage coil. You look at the voltage coil. So one end of the coil is connected at Y and other end of the coil is connected at B. So we can have VYB. Right? So this is nothing but line voltage. That means from this point to this point. Okay, line voltage. See, using this potential coil, we are calculating the voltage. And similarly, what is the line current? That means since it is connected at Y, so the line current becomes IY, because the current coil in the second wattmeter is connected to this Y. So IY, and cos, again angle difference between VYB and IY. So let us call this equation as 2. So now we have obtained two equations using two wattmeters. So using first wattmeter, we have got VRB IR and cos of this angle. This angle is nothing but angle difference between VRB and IR, and the second wattmeter reading is VYB IY and cos of this angle, and this angle is what? The angle difference between VYB and IY. Okay, so now we have obtained two equations. Now based on these two equations, we are going to have the Phasor diagram, and before Phasor diagram, so we need to express the line voltages in terms of phase voltages, as we have discussed in the previous session. So let us have the equation. So VRB. So VRB is the line voltage. So now we are going to express line voltage in terms of phase voltage. And what are the phase voltages here? What are the phase voltages? Phase voltage is nothing but the voltage is measured across this phase, across the load, right? Across the load. And how we can express V and VRB? So VRB can be expressed as, so VRN, okay? So that means R2, this R2 neutral point, and from neutral point to B, okay? Remember, this VRB, it is a line voltage, that means it is measured between this R to B, and this can be, so now we are trying to express VRB in terms of the phase voltages, and the phase voltages are, that is from R to N, okay, neutral point, and from neutral point to this B. So now we can have the equation as VRB is equal to VRN minus VBN. So to understand the same equation, so again we can, so you can go through the previous session, so you will understand better. So VRB is equal to VRN minus VBN, and similarly, so VYB can be expressed as VYB is equal to, so VYN minus VBN, right? So here, because our aim is to find the angle difference between VRB and IR in the first case, and VYB and IY in the second case. Now, so considering the first equation VRB, and we have got this equation, and so here, so VRB is expressed in terms of VRN minus VBN, and so to draw the Phasor diagram, always we should start with the phase values, right? As I have already explained in the previous session, always we should start with the phase values. Now what are the phase values here? VRN and VBN. So let us take this VRN, and VRN, angle difference between VRN and IR, okay, the current IR, let us assume this as phi, Okay, so I'm just assuming the angle difference between this VRN and IR as phi. And in the second case, so let us assume, so VYN, okay, I'm considering VYN since it is the phase value, phase voltage. So VYN and then IY is equal to phi, right? So here we are just assuming the angle difference between VRN. So why we have chosen VRN? Because we have to start the phasor diagram with the phase value. So since we have to start with the phase value, so we have considered angle difference between VRN and the IR. Okay, IR as phi. So this is just an assumption, phi, and similarly the angle difference between VYN and IY as phi, right? So now based on these equations, so we are going to see the phasor diagram. Okay, so we are going to have the phasor diagram, and you already know that, you are already familiar to draw the phasor diagram. So always we should start with the phase values. Let us consider this as VRN initially. So initially we have VRN and VBN, and another one is VYN. Okay, so these three are the phase voltages, isn't it? So VRN, VBN and VYN. So now let's see the first equation. So we have VRN over here. Okay, so of course we have VRN and we have minus VBN. So this is VBN, and where we should have minus VBN, so we need to project this line in the opposite direction such that so we get minus VBN. Okay, so I'm just trying to project this in the opposite direction to get minus VBN. So look at this, this is VBN and minus VBN, isn't it? And what is the left hand side? So equation, so we have VRB, that is the resultant one. So where we should draw this VRB between these two. So because VRB is the summation of VRN and minus VBN, so here we are going to have in between, exactly at this point, at the half of this line, since VRB is the double of this VRN and VBN, because it is a summation of these two, so we get VRB, right? So we have VRB. So here we have VRN and minus VBN, and of course we have VRB, isn't it? Now, so we need to have this phi. So where we can have phi, that means the angle difference between VRN and IR is equal to phi. So we have just assumed this as phi. So now we have VRN and IR, where we should draw IR, and here you can make an assumption saying that IR lags. Okay, so IR lags VRN by some phi. Okay, IR. So here we are just assuming the current lags voltage. We are just assuming here current lags voltage by some phi, angle phi. So that means here we are going to have this IR. We are going to have IR here, okay, with some angle. So that means the IR lags VRN by phi. So we are just considering this as phi. Now our aim is to find the angle difference between what? VRB and IR. Our final aim is to find the angle difference between VRB and IR. So that means what is the angle at this point? The question is, what is the angle at this point? Okay, so look at this, what is the angle here? So we know that the angle difference between VRN and VYN is 120 degree, isn't it? Because the angle difference between VRN and VBN is 120 degree, and similarly from here to here 120 degree, and from here to here 120 degree. So okay, look at this carefully. Angle difference between VRN and VYN is 120 degree. Now the angle difference between VRN and minus VBN is is 60 degree, because since this is exactly half of these two lines, okay, minus VBN is exactly half of this VRN and VYN. Now, so we get the angle difference between VRN and minus VBN is 60 degree. Okay, and so which is the half of these two lines? That is VRB. Now what is the angle difference between VRN and VRB? The angle difference between VRN and VRB is 30 degree. Clear? So here the angle difference between VRN and VYN is 120 degree, and the angle difference between VRN and minus VBN is 60 degree. Since this VRB is exactly half of this VRN and minus VBN, the angle difference between VRN and VRB is 30 degree. Now what is the angle difference between IR and VRB? Okay, now the question is, what is the angle difference between IR and VRB? So this is 30 and this is 5. So this angle difference between VRN and VRB is 30 degree, and angle difference between VRN and IR is 5. So we have just assumed this as 5. Now what is the angle difference between this IR and VRB? So remember, the angle difference between VRB and IR is equal to 30 minus 5. This 30 minus 5, okay, is nothing but what? Angle difference between IR and VRB. So that means it is 30 minus 5. 30 minus 5. Okay, 30 degree minus 5 is nothing but the angle difference between IR and VRB. Right? So I hope this part is clear. Now let's get into the next equation. So we have next equation, that is VYB is equal to VYN minus VBN. Okay, so here we have VYN. So where do we find VYN? So this is VYN, and where is minus VBN? Of course already we have minus VBN. And which is the resultant one? The resultant one is what? Which is VYB. So now this is VYB. Clear? So we have VYN minus VBN, and the resultant one is VYB. Okay, the line voltage. Now, so we should have this VYN. Okay, so we have already of course VYN, and so IY. So where should we draw IY? So already I have indicated the current lags voltage. So current lags voltage. So again IY lags VYN, okay, by 5. So where should we draw IY? Because since IY lags VYN by 5, so IY lags means what? After the voltage starts, the current starts later, okay, with some angle phi, So this is nothing but IY, isn't it? See, even at this point, so IR lags VRN. Right? So after this line, so you have IR. Similarly, IY lags VYN. So after this voltage, so we have IY with some angle phi. Now the question is, so we need to find out the angle difference between VYB and IY. Okay, so we need to find the angle difference between VYB and IY. So where is VYB? So we have VYB over here and IY is here. So we need to find the angle difference between IY and VYB. So what is the angle? Okay, what is the angle difference? Again, so let's go back to the previous similar discussion. So what is the angle difference between this VYN and VRN, which is again 120 degree. Okay, and what is the angle difference between VYN and minus VBN, which is again 60 degrees. So of course this is 60 degree. And what is the angle difference between VYN and VYB, which is 30 degree. Okay, so here the angle difference between VYN and minus VBN is 60 degree, and since this VYB is exactly half of these two lines, the angle difference between VYN and VYB is 30 degree. Now the question is, what is the angle difference between IY and VYB? So the angle difference between IY and VYN is phi, and the angle difference between VYN and VYB is 30 degree. So if we just add these two, then we would be getting the angle difference between IY and VYB. So now the angle difference between VYB and IY is equal to 30 plus phi. See, look at this. This is 30 and this is phi. So we are going to find the angle difference between IY and VYB. So we get 30 plus phi. So in the previous part we have got 30 minus phi, but here we have got 30 plus phi. In the first case 30 minus phi, in the second case 30 plus. In this case we have considered the current lags voltage, right? But in the other case, if you consider current leads voltage, that means IR leads voltage by phi, okay, IR leads VRN by phi, then so we get in this case 30 plus phi. And if you consider IY leads VYN by phi, then so we get 30 minus phi, okay, vice versa. If you consider current lags voltage by phi, then we get, in one case we get 30 minus phi, in another case we get 30 plus phi. And similarly, if you consider current leads, instead of taking lags, if you consider IR leads VRN, so instead of getting 30 minus phi, so we would be getting 30 plus phi, and instead of getting 30 plus phi in the second case, then we would be getting 30 minus phi, so vice versa. Okay, so that means anything can be considered, either current lags voltage or current leads voltage. Now, so we are going to substitute this equation, these two equations, in the first and second equation, that means equation 1 and equation 2, to obtain the total power. So now the total power is equal to, we know that total power is equal to W1 plus W2. So what is W1? W1 is equal to, so VRB IR and cos of the angle difference between VRB and IR. So what is the angle here? The angle is, so 30 minus phi. So that means cos of 30 minus phi, okay, so plus, so what is W2? W2 is VYB and IY. So what is the angle difference at this point, which is cos of 30 plus phi. So now we need to simplify this equation, and now the total power is equal to, so we know that this VRB and IR, so these two are the line values. So straight away I can write this as IL cos of 30 minus phi, okay, plus IL cos of 30 plus phi. So we have got total power is equal to IL cos of 30 minus phi plus IL cos of 30 plus phi. So let's simplify this equation. So in the next step, so total power is equal to, so VLIL, right? So I'll take VLIL common from these two expressions. And so what is cos of A minus B? Cos of A minus B is cos A cos B, okay. So cos of A minus B is cos A cos B plus sin A sin B. So here we get cos 30 cos phi plus sin 30 sin phi, right? So, and in the next case, so we have cos of A plus B, cos of 30 plus phi. So cos of A plus B is cos A cos B minus sin A sin B. So plus cos 30 cos phi minus sin 30 sin phi, right? So look at this equation. So in this equation, so plus sin 30 sin phi minus sin 30 sin phi gets cancelled. So total power is equal to, so VL IL, it is 2 times, right? So 2 into cos 30 cos phi, and we know that So cos 30. So into 2 into what is cos 30? Cos 30 is equal to root 3 divided by 2 into cos 5. So 2 gets cancelled. So remember the total power is equal to VL IL, right? So VL IL root 3 cos 5, or finally we can have the total power as root 3 VL IL cos 5. Hence this equation is proved. In the next session, so we'll see the power, okay, we'll see the total power, how we can calculate, how we can measure the total power in delta connection. Thank you.